All right. So, okay. So let's dive in here to 1.5. We're going to talk about parent functions and transformations, basically. So let's talk about what a family of functions is.
Hey, can I
This
go
is,
grab my notes really fast from the printer?
yes. A family of functions is basically a group of functions which have similar qualities. So for example, parabolas, that's a family of functions, but one parabola might have a different, equation than the other. A parent function is the simplest way to write the equation of a family. So for example, if we are talking about parabolas, right, then the parent function would be y equals x squared, okay? And then, different variations of it, could be something like this. Okay, so let's talk about parent functions, right? Let's talk about all the different types of functions. Okay, so first we have what we call a constant function. And a constant function, looks like a horizontal line. So examples would be, for example, f of x equals 3, y equals 5, and so on, right? So, this could be, let's say, y equals, I don't know, 4.5. It's a constant function. It's a straight line. Next, we have what we call an identity function. These are where your linear functions come in. When we have f of x equals x, the reason why it's called an identity function is, if x is 2, y is 2. If x is -4, y is -4. It's an identity, right, between x and y. And then the family is the linear function. Quadratic functions, these are everybody's favorite types of function, right? The equation for the parent function is f of x equals x squared. And, these are the ones that give you a parabola. Next, you have a cubic function. F of x equals x cubed. And this is what, the parent function looks like. F of x equals x cubed. So one thing to notice is the x squared, right? If you only have f of x equals x squared, this is an even function. And then the y equals x cubed is an odd function, right? But, so all parabolas, right, will have the same end behavior, either both up or both down. And then all cubic functions will have opposite end behavior, right? Okay, next, absolute value function. Okay, so this is what I mean when I say we're just going to give things a little bit of a twist. You all know what an absolute value function looks like. It looks like that V when you graph, right? But let's give it a calculus twist, right? Let's give it that pre-calculus twist. Okay, so now that we've learned piecewise functions, take a look at this absolute value function. This is f of x equals absolute value of x, right? That graph. But look, do you see how there is a split down the middle in how this graph looks? What's more is, with that purple vertical line, I can divide this region into two, where x is greater than or equal to 0, or x is less than 0, right? I just divided the x and y coordinate system into two. Now look, if I were to just take this line, is that the same as the graph for y equals x? It is, right? And if I were to take the other half, is that the same as y equals -x? It is. So you know what? I can write f of x equals absolute value of x in two ways. That's one way. Or I can write it like this as a piecewise function. And that's what we need for calculus, right? In calculus, that's the way we look at things. One of you guys is probably going to ask me, how do you know where to put the equal, right? Less than or equal to? It doesn't matter as long as you just close one of them. You're done.
That was my question.
Yep, I know.
Can they both be closed?
No, both cannot be closed because then it will not be a function anymore. Okay? If they're both closed, that means it doesn't pass the vertical line test. Okay? All right. Next, we have the greatest integer function. It's also called a step function. Okay? Lots of things mimic, this is one of my favorite functions. Lots of things mimic this. So for example, like your age and your time and your grade level, for example, right? Like, from like 0 to 1 years, you're in, 8th grade. And then 1 year to 2 years, you're in 9th grade. And then, 2 to 3 years, you're in 10th grade and so on, right? So what it is you just have integer values of y. So you don't have to know too much about it, just that it exists. That's what it looks like. But what's the domain of that function? You can just yell it out if you know. Or you could be wrong. I really don't care.
All real numbers.
All real numbers. And then what's the range? Oh, yikes. What's the range of that? Is it a continuous range?
No, it's only integers.
It's only integer values, right? So the range is only integer values. Okay, so moving along from that, okay, let's talk about some translations, right? Vertical and horizontal translations. So if I have a function, y equals f of x, and then if I have y equals f of x plus k, that plus k moves the graph up or down, okay? So here, if I have, if this one is equal to y equals x squared, then this is y equals x squared, I don't know, plus 3. Similarly, if I have y equals x squared minus 4, then the graph moves down 4 units. Okay? Now, what about a horizontal translation? A horizontal translation looks like this. When you have a plus or minus added to the x itself inside parentheses. So again, if this is y equals x squared, then take a look at this one. Y equals x minus 3 squared. In this case, right, it's a minus 3, but look at how you can tell what the translation is. You take that term, set it equal to 0, solve. Now you get x equals positive 3, meaning it moves 3 units to the right. So here, what would be a proper or a probable equation for that red one? Y equals what, would you say? Anybody want to guess? Paul?
Would it be y equals x plus 3 squared?
Yep. X plus 3 squared, right? Because if you take the x plus 3 and set it equal to 0, then you get x equals negative 3, moving it to the left. So those are horizontal translations. Okay, Now, how much of it do you need to know to graph? So listen, you should be able to graph some of these functions at a relatively basic level without a calculator. Because later on in calculus, you're going to be given a function, another function, you have to graph them, see where they intersect, and look at the region that they cover, basically. All right. So you have to sort of be quick on your feet with them. So I have x cubed as my parent function here. I know that x cubed looks like that, you know, like that vertical snake almost. Now I have x cubed minus 3. Lots of ways to do this. I know that x cubed was centered at the origin. X cubed minus 3 moves that center point down 3 units. So there's going to be that center point, right? Now, how do you graph the rest of this? It's up to you. One way is just pick point. When x is 1, right? Y is -2. Okay? When x is 2, y is 2 cubed minus 3, 5. And then you have to mirror the points to the other side, right? Okay, another way to do it is this. Another way to do it is this. Since this is an x cubed, if you move over 1 unit, you go up 1 cubed. If you move over 2 units, you go up 2 cubed. You could do it that way as well. Does it matter? No. Okay, whatever works for you. This one,
on
we
these
move
graphs,
to the right 4 and up 2.
on these graphs, do you want us to have points or can we just draw the line?
I want you to have 2 to 3 points.
Okay.
Like the center point and then like, you know, 2 more left and right. So
Okay.
they like, it's not NASA precise what I want, but like it's, you have to have some precision because you have to later match it with something else. Okay, so this moves over to the 4, over 4 units and up 2. And let's do this using the, you know, the cubic factor. So if I go over 1 unit, I go up 1 unit. And then mimic on the other side. Go to the left one, down 1. Now if I go over 2 units, I go up 8. Here. And then down 8 here. 1, 2, 3, 4, 5, 6, 7, 8, right? Okay?
I have a question.
Yes.
How do you know how many points to go like up and down when you're drawing your line?
So definitely the center, and then do 2 more, right? 2 to the left, and then mimic 2 to the right. Sometimes you won't even be able to do the second one because it'll get too high, right? So like if you're going way above like the -10, +10, you don't have to do it.
Because
Okay.
I'm saying like how'd you know to do 6, 10, like for the point at the top?
How do I know how to do it? Well, because I kind of like, it was still within my -10 to 10 limits, so I did it. You know what I mean? If you see that that second number is becoming way too high of a number, just say, okay, that means it's gonna go straight up pretty quickly and graph it that way. Okay? All right, reflections. If there is a negative in front of the equation, then the graph is reflected around the x-axis. So if this is y equals root x, this would be y equals negative root x. Similarly, if this is root x, if I have a negative inside next to the x, then it will be reflected along the y-axis. And what does that look like? If I have y equals root x, do you see how the x values that go in there, it's only possible when the x values are from 0 to infinity, right? So the right half of the graph. But now, if I were to do y equals the square root of negative x, what values are now possible for x? Can I put in positive numbers now? No, only negative numbers, right? So now this only works for these negative numbers, right? So that's how it translates to the left. Okay, let's graph some of these.
Wait,
Okay.
wouldn't that be one of those zeros need to be a parenthesis, not a bracket?
Oh, so in this case, it's like two different graphs drawn on one, so it's okay. It's not that one graph has two values. You see what I mean?
Yeah.
Yeah. Okay, so we're gonna use the graph of root x to graph these. Okay, so what does this look like? First of all, it's translated up 4 units. And then this says a reflection. So first of all, what does y equals root x look like? Well, it looks like one of these, right? Here. So the way I would graph root x is when x is 0, y is 0. When x is 1, y is 1. And then I put in like perfect squares. When x is 4, y is 2, and so on. Okay, so here, the graph has moved up 4 units. Here. Okay. So now, when x is 1, right, what's y here? It's -1 plus 4, so 3. Okay, and then I wouldn't plug in x equals 2 because I don't want to get decimal points. I plug in things that I want to work with, right? So like I plug in x equals 4 and I get -√4 plus 4. So that's just 2. Oh, sorry, 2. Okay. And then what else would you plug in? I would plug in 9, right? So -√9 plus 4, that's 1. So that's what that looks like. All right.
Could you also just do this, like doing the translation and then putting in a regular parabola at that like specific point? Do you know what I mean by that?
Yeah. Yeah, here's another way I would do this. I would say, okay, I start from here, right? And then I would say this is a square root, right? So if I go over 1, I would go down √1, which is 1. And then if I go over 4, I would go down the square root of 4, which is 2. You see what I mean? Or if you can think of a sideways parabola, right? 1, 1, 2, 4, that works too.
Right, because I just see that. I think, okay, go up 4. It's the lower half of a sideways parabola because of the negative, and then just put in a regular parabola. Is that fine?
That's perfectly fine. This is exactly what I mean, is I want each of you guys, because listen, in a, with Precalc honors, usually, people are, they have their math ways down, right? So find a way that works for you. That's why I do each one in a different way almost, just to show you guys, you don't have to stick to one, right? Whatever works for you. The end game is know what this thing looks like, so you're able to combine it with another one later. Okay? So here, this graph moves to the left 1 and up 2. So left 1 and up 2, that's here. Okay, now, let me show you guys, and you can definitely pick points, but let me show you guys what I was talking about before. For this one, this is a square root. So if I go over 1, because there is a negative, I'm not going to go up, I'm going to go down the square root of 1, which is 1. And then if I go over 4, I would go down the square root of 4, which is 2. Okay, yeah, I can tell there is some Wi-Fi issues happening. Okay, so that's how this looks. If you were to plug in points, right? We did x equals 3. What's another one you would plug in? I would only plug in numbers that would give me a perfect square underneath. So I would plug in like x equals 8. Okay, so I have negative 8 plus 1 plus 2. So that's another thing. Negative 3 plus 2, so negative 1. All right?
Miss Malikian?
Yes.
So these A and B, they're both the reflection.
Mm-hmm.
Oh,
Yeah.
so what happened with putting in a negative number if it's a reflection, and putting in a positive number if it's the non-reflection?
So that was when it was reflected along the y-axis. So if it was like the square root of negative x. Not
Oh, I see. Okay.
Yeah. Okay, vertical dilations and horizontal dilations. Normally, I really go in detail with these, but I'm not going to this year. So basically, the factor of A in front gives you vertical or horizontal dilation. It makes the graph wider or narrower, okay? What you need to know from them is how to graph them. So let's take a look at this one, right? G of x is negative 4x in an absolute value. So there is no horizontal or vertical reflection here. This is an absolute value graph. So what do? You see an absolute value function, you know it's going to look like the V. Vertex is at the center here, at the origin. Okay, and then do whatever works for you. You want to plug points in? Let's plug points in. When x is 1, y is negative 4. And we know it's mirrored on the other side. When x is 2, it's negative 8. And there. Okay, do you see how it's narrower because of this? Okay, then just the absolute value of x. This, because it's less than 1, makes the graph wider. And again, this is a parabola, right? So you have to graph a parabola. The vertex is here. And then you decide which points you want to put in for this. You want to take x equals 1, fine. Then we get 1/4, 1/4. What if x equals 2? Then here I get 2 squared is 4, divided by 4 is 1. Okay. Okay, so look, x is 3, right? When x is 3, I get 9/4. I don't know about you. That's just not a very good number to graph, right? Because where is 9/4? It's something over 4. So that's when you can do a little bit of estimating and just sort of, draw your graph like that. I don't need NASA precision. I need you to know that this is a parabola, where it's centered, and generally how it looks, okay? So 2 to 3 points is fine. Okay, these are more important, I think, right?
Could-
Look, yeah.
Could we skip over the 9/4 and go to just 16/4 because it's makes it a little bit easier to graph?
Absolutely, yeah, and you could just do the fourth, yeah. Ben?
Could you go up for 1 second?
Yes.
Okay, thank you.
Okay. Okay, piecewise function. I have a partition at 0 and I have a partition at 3, right? So, here's 0 and here's 3. What this does is it separates my graph into 3 different regions, my grid into 3 different regions. So now I want to graph every single equation in its own domain. Okay, so for equation number 1, that's this one. Which partition does that one touch? X equals 0, right? So the first thing you want to do is plug in that endpoint 0. And you get 3. Sorry, 3. And that's an open circle. So at 0 and 3, I put an open circle. Okay, now I need to graph in that region -x plus 3. Again, it's up to you how you want to graph it. It's a linear equation. So you want to pick another point? Sure, let's pick another point in that domain. So we pick -1. What does that give you? 4. Right? So that's what that looks like. Okay. Graph number 2 has an equation of 2x. Where are its endpoints? 0 and 3. You have to plug in both of these. 2 times 0 is 0. So at 0, y is 0, closed circle. 3 gives you y equals 6, open circle.
Why is the first one closed and the second one open?
Because here, this is closed and this is open. And then in the third region, we're graphing a square root function. What's the endpoint? 3. So first you must plug in 3. X equals 3. This gives you root, what's wrong with it? Root 4, which is 2. So x is 3, y is 2. Closed circle. And then I have a square root here, right? So let's plug in values for x that will give me a perfect square underneath. So like 8, right? When x is 8, y is 8 plus 1 and a root 3. Here. Okay. Questions? Comments, concerns?
So for this one, the origin of this, not the origin, I forgot what it's called. The vertex, that's what it is. The vertex of this parabola would be not visible on this graph, right?
Absolutely, yeah, it's an endpoint. Since it's not a parabola, I mean, potato now. It's so the endpoint of this would have been
Would have
here.
been to the left one, right?
Yeah, it would have been here. So it would have looked like that, right? But now it's not visible, correct, because it's not in our domain. Okay. So take a look at that next one. We got like some absolute value action happening, right? I have a partition at 0. I have a partition at 2. Okay. Again, I have a region 1, 2, 3. Okay. In region 1, right? So now I have an absolute value. So you have to be kind of, I don't know what's the word. Is it woke? I don't know. You just kind of have to like be with it here, right? You have an absolute value. It's x plus 2. That means the vertex, like what Tal was talking about before, be mindful of where all these are. The vertex was here, right? So this would have looked like that in its, you know, in its heyday, right? That's what it would have looked like. But now we've got like restrictions and stuff. So we have to be mindful of that. Again, you have to plug in the endpoint. So when x is 0, y is 2. And it's an open circle here, right? And then this one too, it goes up with a slope of 1. The second one is absolute value of x minus 2. So in its heyday, what would that have looked like? That would have looked like this, right? But we don't want any of that. We only want a little itty bitty part of that. So let's plug in the endpoints for that. It's 0 and 2. So I get -2 and 0. Close that 0, -2, and then open here. Last but not least, we've got that square root function. Okay. The endpoint for that is x equals 2. So that gives me root 2 plus 2 plus 2. So many 2's. How much is that? 4. So when x equals 2, y equals 4, open circle. And this one, you have to give it some, you know, a curve. So again, let's plug in a number that would give me a perfect square underneath. This time, I would plug in 7. So that would be 3 plus 2, 5. And that's how that looks, right? So remember, this too, it had started at like, without the partitions, it would have started, you know, from here. That's what it would have looked like. I'm sorry, -2 and 2. So from here, that's what it would have looked like. Okay, but now we only have the little part of it. And it continues here. Okay. How much of this had you guys done in Algebra 2?
I remember doing this in Algebra 1.
Yeah.
But we did most last year in Algebra 2.